All right, guys. This is for primarily for third and fourth period. Sorry, guys, I've been out the last 2 days. Got a sick 7-month-old daughter. But I did want to give you guys the opportunity to at least see one or two more examples and feel like you could finish the notes, have enough practice to be ready for the quiz on Thursday. So hopefully you get a chance to finish this up before Thursday's class. I did put this one, I believe, this is example 5 on your notes from 4-7. Put it up on the site yesterday, and hopefully you had a chance to start it and try it on your own. I did mark a couple of the givens unintentionally on here, and hopefully you change this R from a T on your paper to an R. So you got segment RA congruent to segment BG, and of course I mentioned the other day that triangle BIG is the bigger triangle on the left. The little triangle in the middle is called triangle LIT, which is the one we're trying to prove is isosceles. And then the larger triangle on the right that overlaps it is LAR. So the givens on your RA congruent to BG, I already marked that on the drawing unintentionally. Angle A and angle G are congruent. There's G and there's A. And the last thing that's hard to mark on here is that LA is congruent to GI. Don't overlook that. LA, this segment over here, LA congruent to GI. So those two pieces are congruent. That should give you enough information to dive right in at proving triangles are congruent. Hopefully you can see right away you've got a side, an angle, and a side, congruent to a side, an angle, and a side of these two triangles. If you were to slide these apart, you'd see you have two triangles with side, angle, side. So I'm hoping you jump right into that. Triangle BIG, congruent to the other triangle. B corresponds to R, I corresponds to L, so RLA, and A corresponds to G. By side, angle, side, and it looks like it would be by reflection. You'd be flipping this over along a line, sort of an imaginary line that bisects T or perpendicularly drawn through T. And then hopefully you're getting good at this. After you side, angle, side, you can use cpctc. Think about what parts of these triangles you need to prove this is isosceles. Some people might jump to the conclusion, well, I want to use this part and this part. These two sides have to be congruent if it's isosceles. Based on the drawing, it looks like LT and IT are congruent. You can't get there directly because LT is not a side of this triangle. TI is not a side of either of these triangles. However, this angle here is a part of this triangle, and this angle over here where I is a part of this triangle. So you could go with angle BIG, this angle here, congruent to angle RLA. And notice the symbols are different on here. There's an angle symbol, there's a triangle symbol. Clearly these are parts of those triangles. So clearly we could use corresponding parts of these congruent triangles to get two angles congruent. And as we talked about quite a bit in the last few days, or at least on YouTube I did, if two angles are congruent in a triangle, then two sides are also congruent. So you then could go to, well, across from I is LT, across from L is TI. Those two sides are congruent. And it's by that theorem. And if you don't know the name of the theorem, you just write. If two angles are congruent in a triangle, then two sides are also congruent. And you write it in your own words. There's nothing wrong with explaining that in your own words. It's called the isosceles triangle theorem. It allows you to get there. And there's still one more step. I think you had 4 steps on your paper. Still one more step on there. We haven't stated that. So this last thing you got to do is state that the triangle is isosceles. And of course you understand it's isosceles because you understand the definition of isosceles is if it has two congruent sides, which is what we just said here, then it would be isosceles. So the last reason would be the definition of isosceles. So hopefully you see the difference between a theorem or a converse theorem and the actual definition. The definition just says if two sides are congruent, then the triangle is isosceles. The converse of the isosceles triangle theorem said if two angles are congruent, you can say that two sides are congruent as well. Alright, the last proof I have for you, I've got all the letters on there that you need. I don't have the numbers. So angles 1, 2, 3, 4, and 5, you'll need to add those onto your paper. And you'll see, as you see on the screen, it can be done in 3 quick steps. And none of those 3 steps are stating the givens. I think it says in your paper to just do the major steps of the proof. And by major, I mean don't state the givens. Don't restate any givens. Save yourself a little bit of time. Just do it in 3 quick steps. Angles 1, 2, 3, and 4 across the bottom. Angle 5 is in the top. This is a very tricky proof to see, and I suggest you pause it right now. If you really want to get this, pause it for a second, tinker with it for a minute or two, see if you can figure out those 3 key steps. And I don't know if you're going to work forwards or backwards here. You know what the proof has to end with. Maybe you start with that. So hopefully you paused it and you tried it and maybe you got some of the stuff right. Think about why I gave you 1 and 2 congruent. Angles 1 and 2 are congruent, so that you can conclude this triangle MED is isosceles with ME and ED congruent, or sorry, DM and EM congruent. That still might not get you anywhere. You know, we just talked about it by the isosceles triangle theorem. If 2 angles in a triangle are congruent, you're also going to have 2 congruent sides. You still may not see this. Think about it, at the end you're trying to get 4 and 5 congruent. How would you transform angle 4 up to angle 5? It's a little tricky to see this, but if you were to rotate it, turn it, you could get N rotated up to G, or angle 4 rotated up to angle 5. This is a rotation. Triangle MEN is being rotated up to triangle MDG. Those are the key triangles you need in this problem. And then maybe reread your givens on here and go, okay, I've got a pair of sides that are congruent. Think about where angle 1 rotates to. And think about the sides we just listed here, and one of those theorems should jump out at you. One of those postulates should jump out at you. You've got side ME, angle 1, and side EN for one of the triangles. There's EN. ME we just proved was congruent to EMD. So you've got a side, an angle, and a side, congruent to a side, angle 3, which is also included up here, and side DG. So EN is really being rotated up to DG. N is being rotated to G. The only thing that doesn't move is point M. Point M is, the angle isn't, that vertex hasn't changed at all. It's just being rotated. This side MD is being rotated over here to this unnamed side, it looks like. Sorry, ME is being rotated to MD to get you a side angle side rotation on there. Tricky proof to see, not a hard proof to write all the reasons on here, but a tricky proof to see because so much stuff overlaps on there. And then of course after you side angle side, you guys should now be experts. You can use cpctc to prove that angle 4, which is a part of triangle MEN, is congruent to angle 5, which is the corresponding part of MDG. So, hopefully you like that. I'm going to put this up. If you made it this long, all 7 minutes and 52 seconds, it's worth your time to maybe check the work on the homework I gave out the other day. It's right there. I will spend some time going over it in class. I didn't include every single reason on these, maybe in the last one, just because they don't quite fit on the screen up here. But I'll talk about this. These are some of the main reasons. You may not have the exact same ones. You may have left out vertical angles here. You might have left out reflexive property. I know I left some of the reflexive steps out of here. But feel free to pause this and check your work. We'll see you tomorrow.